Hi everyone, welcome back to this series. Today we're going to cover linked lists, how to create one, and a little bit more about anonymous structs. So a linked list is where you have one element linking to another element, linking to another element, normally with pointers. And they're often heap allocated because you can have a dynamic size. So first I created this thing, test linked list i32, and we create a linked list i32. Which is simply a struct with a node i32, which is a node i32 is simply up here. It's the data, which is an i32, and a optional pointer to the next node. So it could be null. If it's null, then it's, so for example, you have the first node. We create the first node, which has some data, then I have a link to the next one. If it's null, then there's only one element in the list. All right, so we have a few things here. So we have append, which will create. We'll basically add to the end of the list. So first we create the node using this create node, which will allocate on the heap using the tracking allocator. So I'm using the tracking allocator, like I explained in previous videos, how to see when you're actually allocating memory. I believe what I'm using is the general purpose allocator. So I put the general purpose allocator into the tracking allocator. All right, so append. So first we create the node. And it's a pointer to a node, and then we see if it's the source node. So this, say for example, if the list is empty, then the source node will be null. So let's put it at the start. So we put it at the start here, set the source node to the new node, and then increase the length, and then return. If it's not the first node, then we need to look for the last node, and then add it to the end. So we basically make temp, and we make it this next one, next one, next one, next one, next one, until it's null, and then we set whatever the next node is to the new node and then increase the length. Basically, start at the source node, go to the next one, see if it's null, go to the next one, see if it's null, go to the next one, see if it's null. Oh, it's null, put it there. That's all we're doing. So we append, then print, then we insert at the, so we put 0 at position 0. So insert will simply just look for that position, see if it's in range, and see if it's, and then basically move it along. If it's not in range, then we give an error. So we say position out of bounds if it's null, because it means we didn't find it. So what we're doing is we're looking for the position and we're not looking for a null node. And then when we find that, we put that in. So if it's null, then it's out of bounds. Then we have remove, so we remove an element. Here it takes in the data. So if you put in like 1, 2, 3, and you look for 2 and then delete that is all we're doing. And if you don't find it, then you element not found. But we're simply just saying if the next node data equals data, then break, you found it, and then we just move this along, or here we delete, we delete, so node to delete. So we're looking for the node with the data, and then we find it and delete it. That's pretty much it. And then you have to move it like this. So it's like 1, 2, 3. This is linking to that. You move this to that, link that to that. That's all we're doing. All right, remove index is basically the same, except for it's an index. So we're not looking for data, we're looking for the specific index. So index 1, 2, 3, and then we delete that. So it's basically the same code, other than we're looking for an index. And then of course we have print, which is prints whatever it is. Print length is to show what how big the list is, and then clear will delete everything and then set the length to 0. I'll show you what this does. So we run this, and we so we allocated 16 bytes. We allocate 3 times. If I show you in the actual function, so we append 3 times. So that allocates 3 times. 16, 16, 16. We have 48 allocated. 1, 2, 3 null. Then we allocate 16 when we insert. So we insert and we allocate 16. Then what do we do next? So we print. We insert again. We insert 4 and 4. So 0, 1, 2, 3, 4. Then we remove 2. So 0, 1, 2, we remove the 2, then we remove the 4, I believe, and then we free everything with defer. So defer clear just removes everything. So now we have 0 bytes, so no memory leaks. So the problem with doing this is it only works with one type, it only works with i32. Imagine you wanted a linked list of any type. To do that, you need to create an anonymous struct, which I've kind of covered before. So here I have linked list. So we have basically exactly the same functions. So a linked list is basically a function that returns a struct. and the struct could have any type. So instead of I32, we have a type T, and we put the comp time T is the type. So whatever type we put in it will create that, and also we have a node, which is again a comp time, an anonymous struct, which has a type T. So if we put in U64, it'll be U64. So it's basically, that's all we're doing. So whatever we put in, that will be the type. And it's basically the same other than, so we have const this at this. The problem is the anonymous struct doesn't know what it is. So it'll be something like, when you create it, it's like linked list U64, or linked list U8, or linked list U32, or any type really. It doesn't know what it is. So you basically, at compile time, you work it out and set that to add this. And that's how we can do this, because otherwise, like, it wouldn't work, because you have to say what it is. You have to say what things are in parameters. So we say add this, so it could be linked list U64, linked list I32, depends on the types. Other than that, it's basically the same. We create a node T and then add it. Basically, it's the same, honestly. And then create node is a bit different, because it takes in a T, and other than that, it's basically the same, honestly. Every time we have this, we have node T instead of node I32, or node, I think it was the other one. Or yeah, it's called node I32. It doesn't actually take in a type, just takes in nothing. Other than that, it's pretty much the same. One big difference is here. We basically check if it's a character, if it's a U8, and then print it as a character if it is. So I'll just show you what this is like. I think right now I have this set to characters. So I'll just do this, and then we can run this. So I'm doing exactly the same thing, but here I'm creating U8s and making them characters. So we have ABC, ABC, DABC, DABCDE, or DABCE, DBCE, DBC. So we're just doing exactly the same thing. We're just removing, inserting, and then there's no memory leaks at the end, so 0. Then, say for example, I wanted to make this, let's make it U64. What's kind of strange is when I make it U64, the size actually doesn't change. It always seems to allocate 16 bytes, which I'm not sure why. But say if I make this, say 100,000, 200,000, and then remove, let's remove, say 200,000, and then let's remove the index at 3, and then see this. So now these will be U64, and I didn't change any of the code, literally the same code. So the reason why you make anonymous structs is to make them generic, so you can have any type. You don't need to, copy this and have this like 10 times for every different type in the language. But of course it is a bit more complicated to make something like this. It's not too complicated. It's just the main thing is like how the syntax is quite complicated. Like when you make it linked list. There are lots of things in the standard library. For example, a general purpose allocator. This thing is also an anonymous struct, because you can have a config that could be different depending on what your config is. The iterator I showed last time is also an anonymous struct, because it could have a different type and it could have a different setting, like what's the delimiter? Is it a string? Is it a slice? Or is it a single digit? You choose when you create it. One problem you might have is when you're going to give it a type. It's like a general purpose allocator dot. I think that's the type, something like this. You kind of need to do this, which is a bit complicated. I normally just leave it blank, because it's like you have to kind of really know what it is to understand that. This is a bit more simple, because it's linked list U64. It's pretty simple. But anonymous structs are quite useful to understand if you want to understand the standard library, because a lot of them are. Lots of allocators are anonymous structs, lots of iterators are anonymous structs. So it's good to get used to them. It's good to at least know how they work. But that's all for this video. Let me know if you have any questions. See you guys next time.